Good day, everyone. This is the AIoT group from Jiaotong University. We are happy to introduce the XRF-V2 dataset paper, published in Ubicomp 2025. Bo Lan, Pei Li, and Jiaxi Yin are graduate student with Jiaotong University. Yungpeng Song, Ge Wang, and Han Ding are faculties with the Jiaotong University. Jing Songhan is a professor with the Zhejiang University. Fei Wang initiated and led the project. Last year, we introduced XRF-55, a multimodal radio frequency sensing dataset for 55 class classification. Over the past year, it has garnered considerable attention and has been utilized for experimental evaluation in multiple papers from top-tier conferences such as Mobicom, AAAI, and ICLR. However, each sample in that dataset represents a 5-second action clip. This year, we are taking a step further by proposing XRF-V2, which is a continuous action dataset. We know human indoor action understanding aims to make our environments intelligent by understanding human actions. The most established task is human action. However, HAR's focus on isolated actions limits its ability to interpret the continuous, flowing nature of daily life. What's next in human indoor action understanding for building smarter environments? We think it could be the action summarization task. As shown in the figure, for a person's continuous activities, action summarization can detect the start and end time of each action. Based on these detection results, we can then integrate large language models to generate insights, detect anomalies, for example, falls, missed medication, and summarize behavior patterns. To advance indoor action summarization, a dedicated dataset is essential, but existing options present several limitations. Most datasets are video-based, designed for specific tasks like cooking or outdoor activities. While some indoor-focused datasets exist, they have notable constraints. For example, Ego ADL lacks critical hand and head motion data and relies on audio, which poses privacy risks. Wi-Fi T-Aid, with only 3 participants, 7 actions, and a single scene. XRF-V2 leverages multimodal data, combining Wi-Fi signals and IMU data from 5 wearable devices: smartphones, smartwatches, earbuds, smart glasses, with video recordings. Data was collected across 3 indoor settings: dining room, study room, and bedroom. The dataset includes 16 participants, performing 30 diverse indoor actions, from sleeping to food preparation, yielding over 16 hours of data and 853 annotated sequences. Compared to Wi-Fi TAD, XRF-V2 excels in scale, diversity, and modalities. In the dining room, actions like eating or cutting fruit reflect dietary habits, supporting health monitoring. In the study room, study activities such as typing or reading reveal work and study patterns, enabling smart assistance for time management. In the bedroom, actions like taking medicine and sleeping track health-related behaviors, aiding real-time health interventions. In this slide, we present 3 representative sequences from XRF-V2, one for each indoor scenario. Each sequence typically includes 7 to 12 actions, with individual actions lasting 5 to 20 seconds. These are not random combinations of actions, but rather coherent sequences with contextual and semantic continuity. We recruited 16 volunteers to perform actions. For annotation, we used an automated method. We preset the sequence of actions to be performed and randomly set the start and end times for each one. An automated voice prompt would then announce the next action for the user. Upon hearing the voice, the user would perform the announced action. The preset action sequence, along with its start and end times, was then used as the annotation for the sequence. To achieve precise action summarization, we introduce XRF Mamba, a temporal action localization method built on the Mamba architecture. The Mamba architecture excels at modeling long-term dependencies in temporal data and memory efficient. Novelly, XRF Mamba detects temporal actions in sequences, as detects spatial objects in an image, which both output bounding box of the interests. Thus, we adopt the YOLO framework for our task. Like YOLO, XRF Mamba generates multiple temporal proposals, refined by non-maximum suppression to remove redundant segments. We use the intersection over union IOU between the predicted action time and the ground truth time, referred to as TO, to evaluate the performance of temporal action localization. As shown in the table and figures, XRF Mamba outperforms existing methods. For example, achieves a 5.49 map improvement over Wi-Fi TD, with 35% fewer parameters, demonstrating superior accuracy and efficiency. The visualization results clearly confirm that XRF Mamba delivers more accurate temporal boundaries than other strong baselines. To assess XRF Mamba's performance in action summarization, we fed its predicted action sequences to large language models, ChatGPT-4, Qwen 2.5+, DeepSeek V3 to generate summaries. We introduced a new metric, response meaning consistency, RMC, to evaluate summary quality by measuring alignment with human annotated ground truth for actions and their timing. For example, if a prompt asks, "Did the user walk during this period?" and both ground truth and LLM response answer yes, it's a consistent instance. XRF Mamba consistently earned high RMC scores across all LLMs, supporting the downstream LLM reasoning applications. We have provided more details and all 27 Q&A prompts for action summarization in our paper's appendix. So we tested various device combinations, and results show robust performance even with fewer devices. This proves XRF-v2 supports both multi-device setups and flexible user-selected device combinations. We conducted leave one person out experiments. Additionally, we recruited volunteers to perform a real-world zero-shot evaluation in an unseen apartment. These two results demonstrate that our XRF Mamba has strong generalization capabilities. We envision XRF-v2 dataset could open up new research opportunities across multiple fields. For example, XRF-v2 serves as a key benchmark for action summarization across daily devices. It also supports weakly supervised action localization, learning from category labels alone without precise timestamps. Future work can also explore end-to-end methods. This may involve using LLMs to directly understand and summarize raw Wi-Fi and IMU signals. Besides, XRF-v2 dataset provides continuous 2D pose data, enabling pose estimation, tracking, and prediction. We also plan to extend the dataset to include 3D human pose, 3D human mesh, and densiposa data. XRF-v2 can also serve as a high-quality resources for developing and evaluating synthetic IMU and Wi-Fi data generation techniques. It also supports multimodal learning, bridging IMU, Wi-Fi, and video. Please contact Fei Wang via email for discussion and communication. We look forward to feedbacks and collaboration. Thank you for your attention.